Okay, so we're going to continue more with graphing. So we'll have like an alternate way to do some graphing here. So if p of x is a polynomial function of degree n, the graph of the function has at most n real zeros, thus at most n x-intercepts. So this is the most I can have. So if I have a polynomial that's degree 5, then at most I can have 5 real zeros. At most, I can have n minus 1 turning points. So turning points on a graph are what we call our relative maximum or minimum, maximum, minima, because you remember, graph looks something like this. This right here is your turning points, where we go from increasing to decreasing or decreasing to increasing. So those relative minimums and maximums would be your turning points. So just to show here, this is a polynomial. To the left has degree 5. No, it's a weird polynomial here. So this is the graph of it. This has, like I said, it's a polynomial. To the left has degree of 5, which is the power of my leading term. So when we talk about degree, it is the power of your leading term. We have the maximum number of zeros, which is 5 in this case. I couldn't see my mouse for a second. We see one here, in here, in here, in here, in here. So 1, 2, 3, 4, 5. And then my maximum number of turning points, you see, is 4. So to graph a polynomial, we're going to use the leading term test to determine the end behavior. We're going to find the zeros of the function by solving f for 0. Any real zeros are going to be of the first, any real zeros are going to be the first coordinates of the x-intercepts. So we're saying when we talk about x-intercepts, it's always something, something 0, like 3, 0. Well, then 3 would be a 0 of the polynomial. We're going to use x-intercepts to divide. This is an alternate way of, instead of, using multiplicities, you can divide the interval using those zeros. And then you can use a test point to figure out if it's going to be something that's above the x-axis or below the x-axis. And then we'll find f of 0, because that's going to give us a y-intercept. If necessary, we're going to find additional function values to determine the general shape of the graph and then draw the graph. So we might find a few other points to kind of get a better idea of what the graph is doing, is what we're saying. And as a partial check, we're going to use the facts that the graph has at most, if it's a degree n, then n x-intercepts, and at most n minus 1 turning points. So multiplicity of zeros can also be considered in order to check whether the graph crosses at or is tangent to the x-axis. We can also check the graph with a graphing calculator. Ideally, we'll do this without the graphing calculator. Graphing calculator is just what we'll use, like I said, later on. But at this point, we're practicing trying to figure out what these graphs should look like. Oops. So we would like to graph this polynomial. So first thing first is I need to figure out what my end behavior is. So as we see with this leading term, end behavior is going to be something that's going to look like this, because we have a odd power and a positive coefficient. So we'll just put a little note here like this. We know it should be doing something like that. So the next thing we want to do is we want to find our zeros. So anytime you do find zeros, just as a reminder, again, we were doing this with quadratics, but once again, you should always make sure that when you're finding zeros, your polynomial is equal to 0. But we would need to factor this. So we're going to try factoring by groups. So here I can factor out at least and x squared, and I'd be left behind with a 2x plus 1. In here, I can factor out a negative 4, would leave me with a positive 2x plus 1. Then we can factor out the 2x plus 1, and we would be left with x squared minus 4, which we can factor further because that is a difference of squares. So we know that factors into x minus 2, x plus 2. So each one of these factors, due to that zero product, means that either this factor is equal to 0, this factor is equal to 0, or this factor is equal to 0. So if we solve, one of my zeros would be at negative 1.5. The other one will be at x equals 2, and the other one would be at x equals negative 2. Okay, so let's just graph these on here. So let's say this is 2, this is negative 2 here. So we have 1 at this spot, 1 at this spot, and then we have 1 at, was it negative 1/2? So right here. Okay, so I made a little chart here. So like I said, we're not going to use the multiplicities this time. We're going to test our intervals. So you could use the multiplicities again if you wanted to, but like I said, this is an alternate method. So what we have here is a couple intervals that are broken up by these zeros. So my first interval is from negative infinity up to negative 2. Then after that, the next one would be everything that was between negative 2 up to the next zero, which was negative 1/2. Then we would have everything in this interval, which was everything starting after the negative 1/2 and stopping at the next zero, which is 2. Then we would start on the other side of 2 and go towards infinity. Oops. Okay. So test point, we need to pick a number that fits in this interval. So as an example, negative 3, something that fits in between negative 2 and negative 1/2. Well, negative 1's in there. Something between negative 1/2 and 2. Well, 0's in there. And something from 2 to infinity. Well, we got 3 in there. So here what I'm going to figure out is what those function values are. Okay. So got a little chart helping me here. But f of negative 3 would give me negative 25. So I know that on this interval, I have to be in the negative area. So I'd have to be somewhere down here. Then next, we'll test that negative 1. So if I have f of negative 1, that's going to be 3. That's positive, telling me I have to be up here now. Then the next interval, if I test that 0, that's going to equal negative 4, telling me once again, I'm down here. And then for my last one, we're going to try that 3. So f of 3 is 35. Okay, let me get rid of some of my extra here. So we're going to get kind of a rough sketch here because we need still to do a few other things. But essentially what we have here is that in this interval, anything before negative 2, I should have negative function values, meaning I'm down here. The next interval, I have to have positive function values. So I would be up here. And I know I have to go back to this other 0, so that's why I know it's going to curve. And then for the next interval that we saw between negative 1/2 and 2, we had a negative value again at negative 4. So we would have been down here. Oops, and curve towards the 0. And then I know I'm positive anything from 2 greater because when I tested a point, it was positive. So that's what testing interval does, is it's really mostly, the main point of it is to tell if things are going to be positive or negative. So it tells me, am I below the x-axis? So here I'm below. Here I'm above. Below again. Or above. And above. Or we could use the idea of multiplicities. So I raised it here, but what we saw was that everything had a multiplicity of 0, meaning that I would cross, cross, cross. So another important part of graphs is we like to know x-intercepts, but we also like to know y-intercept. So y-intercept is the point f of 0. So it happens when x is 0. So we see here at f is 0. So we actually did find this point already. We'll just do this again. What we see is that we would just left with -4. So if we were to now scale this, 1, 2, 3, 4, we know that I'd be down here. Oops. Try to, there we go. That did not quite go well. Got to do it like this. There we go. So we go like this, we come up, we go down, we know we have to go down, touch this point, and then go here and cross through. We could find a few other points just to kind of gauge where this might be. And actually, when we picked a point in this interval here, it was about at 3, I believe is what it was. So another point we did have when we were testing points is that -1 and +3, sorry. So that's that part about having extra points, is that we already kind of had some extra points when we were testing the interval. So we know that we should come up and at least hit this point. Sorry, it's hard to do this with my board. Up, down, through, and through like this. And you can graph this function on your own, but this is basically pretty close to what the actual shape looks like. So as we see right here is just that same graph again. So ours was pretty close with just a few points. This example here actually used a couple extra points. Like I said, we kind of knew what was going on here and here. That was pretty much more than enough for us right now. Okay. Oops. So on number 7 and number 8, all you're doing is you're just using this method once again. So you need to figure out the long-term behavior, then factor to find your zeros, then make that interval and try to figure out, and find test points in those intervals to figure out if we're below the x-axis, above the x-axis, fire and y-intercept, and then you might want to just find a few extra points just to flush out the graph. So hopefully you took a couple minutes and worked on that. So we got 4 terms. We're going to try factoring by groups again. So once more, I can factor out a x squared. Oops. So if I factor out my x squared, I'm going to be left with x minus 2. And then here I could factor out a -9, and I'd be left with x minus 2 again, because I'm factoring a negative from both numbers. And remember, this has to equal 0, so this factoring actually makes some sort of sense. Factor out the x minus 2, and I'm left with x squared minus 9. So we're going to get x minus 2, and then difference of squares, so we get x minus 3, x plus 3. So we can see here that my zeros are going to be at x equals 2, x equals 3, and x equals -3. There we go. 2, 3, -3. Also, we need long run behavior. So that is based off of this here. So what we're seeing is that we have a positive coefficient, because remember, it's just a 1 out here, and a odd power. So just like the last one, we know the long run behavior is going to look like that. So what we're going to do next is we're going to test those intervals. Okay, so if you remember, what we have here is your intervals. So we have an interval of everything that comes before that first 0 at -3. So that's from -infinity up to -3. Then we look at from the other side of -3 up to the next 0 at 2. Then 2 to the next 0, so 2 to 3. And then we have 3 to infinity, because that's everything on the other side of that 3. Then we need a test point. So the test point has to be something in an interval. So this one goes from -infinity to -3. So we could try -4, -3 to 2. Well, let's try 0 again. We got 2 to 3. So we might have to try like 2.5. And then we got 3 to infinity. So we can try 4 again. And then here we just want to find those function values. So with the -4, that's going to give me a -42. So we know that right now that we would be below the x-axis. F of 0 is going to be 18. That's positive, telling us we'd be above the x-axis. Excuse me. F of 2.5 is going to be about -1. Oh, sorry, it's exactly -1.375. So because that's negative, that tells me I'd be below the x-axis. And the last one is just +4. So F of 4 would end up equaling 14. And this is above, I don't know what I was trying to write there. This would be above the x-axis. So like I said, we have a general idea now that it would look like this. Then it would be negative those ends. We said it was positive between -3 and 2. And then it was negative again from 2 to 3. So we want below, above, below, above. Okay. So some important points that we need to put on here. So right now we actually have my y-intercept. Because y-intercept is when f is 0, which we have right here. So we know that'd be 18. So let's scale that, like this is 10, 20, 30. So 18 would be right about here. Then we have a few other points to kind of help us with some things. So we know at -4, I'm about at -42, -10, -20, -30, -40, -50. So at about -4, I should be somewhere around here. So it's just give me some points to kind of flush this out a little bit. Then between at 2.5, we're like almost still on the x-axis. We're just below it. And then here at f of 4, then we hit 14. Okay, so let me get rid of my dashed lines. So if you want to save yourself some work, your book kind of wants you to like look for all these other points. Well, if you're careful with how you fill out your chart here to figure out if we're above or below the x-axis, it will give us some points. And somewhere inevitably you should be able to put 0 and get that y-intercept. Okay, so we're above here, down touch, up through here, and down through that point. So that's roughly what your graph would look like. Okay, so for 8, this one's factored for us. So I had brought this up once before. So this is the power of 2, 1, and 3. So if I add those powers, I'm going to get 6. So this is my degree. So it tells me that if I factored this, I would have a x to the 6th. And then we have this negative out here, so this would tell me it would be negative. So we know this would be something that looked like this for end behavior. But by testing intervals, we don't really need to look for end behavior. So we know that my zeros would be at, because I have just x here, x equals 0 would be 1. Because I have x minus 3, well, x equals this, or sorry, x equals 3 would be 1. And then because we have x plus 2 is one of my factors, that tells me I have another 0 at x equals negative 2. So we got one here, here, oops, sorry, wrong side, here, and then negative 2. All right, so we just need to do some point testing. I'm trying to grab the right tools. There we go. So we'd have our interval. So anything that came before this negative 2, that would be from negative infinity to that negative 2. Then from negative 2 to the next 0, so negative 2 to 0 is another interval. From 0 to this 3, my next 0, that's another interval. And then from 3 to infinity. So your test points, something that fit in this interval would be negative 3. So 0 happens to be graphed for us, so we don't have to find that y-intercept. That's my y-intercept. So we're going to have to pick something here. So negative 1, 0 to 3, we can pick 2, 3 to infinity, we can pick 4. And then we just need to figure out what our function value is. Okay, so we would have f of negative 3 is going to be equal to 54. So that's going to be above the x-axis. Just a second. Just a second, gotta fix something here. All right, sorry about that. I accidentally put in 2x squared instead of cubed. So this would actually be negative 54. F of negative 1 is equal to 4. F of 2 is equal to 256. And then F of 4 is going to be equal to negative 3,456. But we know this first one's telling us that I'm going to be below the x-axis. I'm going to be above here because it's positive still, so I would be above again. And then here I would be below. So kind of you see my points are a little all over the place. So at negative 3, I'm not sure what I'd scale this to. I think we'll just have to give up because my points are really small and really big. We'll just kind of give you a rough idea what this should be. But I'm below here, and then here I'm above, but I have to come back and touch. The next interval, I'm above again. So that means I have to stay above, then come here, and then I go below. So this is the part where the multiplicity comes in handy, is that this multiplicity was a cube. So what I really know it should be doing here is acting more like a cubic. So it should be like coming up, flattening a little bit, then passing through. Like I said, that's a rough idea of the shape. Some of the other things we know is that because this interval here, or well, comparing these intervals, this one had a small number, this one has a big number in that interval. That would also tell me that this part right here, so this would be a little bump. This one should be a big bump because I have to go be able to reach up to 256. So we should be looking at like, it's a little more like this. But if you have the general idea of the general gist is what we're looking for, that you know that overall it should be opening down, you know where the zeros are, you know that it should be crossing at 3 and it should be crossing at -2, but it should be bumping at 0. That's more than enough. Like I said, some of this is just a little extra flavoring to get your graph a little more accurate looking.